Good day, bright physics students. Now we're done with our last video lesson about this chapter, which talks about work, energy, and energy conservation. So in this video lesson, we will try to understand the concept of energy conservation, and on the last part of our video lesson, we will talk about power and how is it related with the idea that we have now with electricity. So without further ado, let's begin. And the best way to start our discussion with energy conservation is to understand the concept behind conservative and non-conservative forces. So, we have here a demonstration of a book that experiences a certain type of force. So, before identifying what type of force was that, let's try to know first the dimensions that will be that is present in our demonstration. So the mass of the book, let's assume that the mass of the book is 4 kilograms, and the displacement that will be made by the book eventually is equal to 40 meters. Alright, so now, since we're talking about conservative and non-conservative forces, the force that we wanted to identify if it's qualified as a conservative or non-conservative force is the force due to gravity. Alright, so now let's assume that the physics textbook is located 40 meters above the ground. And because of a certain force, so this is the initial position of the book. So because of a certain force, and that force again is the force due to gravity, it is being pulled downwards, alright, up to the level ground. Alright, so this is now the final position of the book, which is 40 meters from its initial position. Now, since this is the force due to gravity, that is the direction of the force due to gravity, the first question that we need to answer is, what is the direction of the displacement? So the displacement of the book in this scenario is also downwards. Alright, so it has the same direction with the force due to gravity. The next thing is to identify if the force due to gravity is really a conservative force. Okay, we need to look at the work done by this specific force. So, if we can still remember from the previous video lessons, work is equal to the dot product of force and displacement. And in order to remove the dot product symbol, we remove the directionality of these vectors. So we try to get only the magnitudes of these quantities. So the formula, or the final formula for work, is equal to FD cosine of angle theta. So the second question, after identifying the direction, so these are the questions, alright, direction of the displacement. The second question is to identify the magnitude of angle theta. Magnitude of angle theta. And if we can still remember from the discussion of work done by a constant force, angle theta is defined as the angle between two vectors. And in this case, the vectors that we are trying to describe here is the force vector and the displacement vector. So let's say that these are the two vectors. Alright, so the angle theta is located at this point. So that angle theta is the angular displacement between the force vector and the displacement vector. So in this case, let's go back to our scenario. If the force due to gravity is pointed downwards as well as the displacement vector, so our angle theta will be equal to 0. And we know that cosine of 0 is equal to 1. So we can simply cancel this one out because this is equal to 1. So work is equal to FD, or the product of force, the magnitudes of force and displacement. Since the force that we're trying to identify if it's a conservative force or not is the force due to gravity. So let's label the force in here in our work formula as the force due to gravity multiplied by the displacement. So if we remember the formula for the force due to gravity, or the weight of an object, that is equal to the product of mass and the acceleration due to gravity. So let's just um, put that into our work equation. So m times g times d. So the mass of the book is given by our dimensions earlier, which is 4 kilogram, and then g is a constant. This is the acceleration due to gravity constant, which is equal to 9.8 meters per second squared. And lastly, we have the displacement done on the book or by the book. So that is equal to 40 meters. So the answer for the work done in this particular scenario is equal to 1,568 joules of work. Alright, so let us remember the questions that are asked in this scenario and the answer of the work done by the book, or sorry, the work done due to the gravitational force. Alright, so let's proceed to the second scenario. So the second scenario is, now that the book is located on the level ground, we shall move the book back to its initial position earlier in the first scenario. So this will be looking like this one. So this is now the position or the initial position of the book in this particular scenario, and this is the final location of the book. Alright, so if you can still remember from the previous slide, this is 4 kilograms, and the displacement again is equal to 40 meters. So now the question is, the force that acts on the textbook to be lifted up into this position is the applied force. But then, again, if we can still remember from the previous slide, the force in trial, if the force in trial that we wanted to identify if it's a conservative force or not is the force due to gravity. So it's not the applied force. Alright, so the force due to gravity in this scenario is still pointed downwards. So we have here force of gravity. Alright, which is again pointed downwards. However, the first question asks about the displacement or the direction of the displacement of the object of interest. So in this particular scenario, since we moved the book upwards because of the applied force, so the displacement done by the book is also directed upwards. So that is now the direction of displacement, and this is the direction of the force due to gravity. So the second question answers what is the magnitude of the angular displacement. Alright, so since we're looking for the angular displacement, which is again found in the formula of work, which is equal to f the cosine of angle theta. So our angle theta in this scenario is, so let's try to move our diagram into this portion. So this is the initial position of the book, so it is lifted up to this position. So that is the direction of the displacement. However, the force due to gravity is still pointed downwards. So this is the force due to gravity, this is the displacement, and the distance between these two, or the angular displacement between these two, is equal to 180 degrees. So that is our angular displacement, and we know that cosine of 180 degrees is equal to -1. Alright, so still the same formula for f sub g. F sub g is equal to mg. So let us substitute the values that we have in here. So we have here 4 kilograms multiplied by the displacement, which is equal to 40 meters, times cosine of 4 kilograms times 9.8 rather. Alright, let me just erase this one. Okay, so since the force in here is equal to the product of mass and the acceleration due to gravity, so let us just write it in here. So 4 kilograms times 9.8 meters per second squared multiplied to the displacement, which is equal to 40 meters times -1. So the answer for the work done by the gravitational force in this scenario is equal to -1,568 joules. Alright, which is similar in magnitude of the previous work done by the gravitational force in the previous slide, but they are opposite in signs. So we have here a negative sign work done, and on the previous slide we have a positive sign work done. But if we can still notice, the displacement taken by the book is the same. So we have here 40-meter displacement. So the initial scenario showed us that the book is located somewhere up there, 40 meters above the ground. So if the force is the same as the direction of the displacement, alright, so that will be our first realization about this scenario. So if the force, if the force is the same as the direction of the displacement, then our work done is positive. But if the force is opposite in direction with the displacement, alright, so the work done, it has a negative magnitude. So these are the observations that we have made from these two demonstrations. Alright, but again, with the same displacement and the same type of force that we wanted to observe, which is the force due to gravity, they have the same magnitude but opposite in signs, which means that the force due to gravity is a conservative force because it only conserved the work done by the book when it moved downwards and when it moved upwards. Alright? So let's try to imagine what happens to the energy of the book when in the first scenario. Alright? So in the first scenario, this is the location of the book, initial location of the book, or initial position, y sub I, and this is now the final position of the book. Alright, that is now the final position of the book. So, if we try to imagine things that are falling from a higher place, going to a lower place, the amount or the magnitude of the gravitational potential energy of that book or that specific object of interest at a higher place is assumed to be at a maximum. But when it moves downward eventually, so as it moves downward, the height also decreases. And if we try to look at the formula of the gravitational potential energy, since mass is a constant property of the matter, G is a constant value for objects that are near Earth or along near Earth surfaces. So this is equal to 9.8 meters per second squared. The height in here in our formula is the only quantity that determines how much is the magnitude of our gravitational potential energy. So definitely if the height is getting lower and lower in magnitude, so which means that it is decreasing in magnitude, that also happens with the gravitational potential energy because they are directly proportional with each other. However, if we try to observe objects that are moving downwards, these objects are increasing in speed, which means that although the work done by the gravitational force, or I mean the gravitational potential energy rather, is decreasing in magnitude, but then we know that the speed of the object is increasing in magnitude, and that is present in the formula of kinetic energy. Mass again is a constant property of matter, so the value or the magnitude of kinetic energy will only vary because of the changes happening in the magnitude of the speed of the object. Alright, so let's try to look at these energy bar charts for better illustration. So this is what I'm telling a while ago. So if the object is located at a higher position or a higher place, the potential energy or the gravitational potential energy of that object is at maximum, which is equal to the total mechanical energy of the system. Alright, and as it moves downward, so as it moves downward, that object, alright, the gravitational potential energy is obviously decreasing in magnitude. However, since the speed of the object is increasing, the kinetic energy of that object is also increasing in magnitude until such time that the potential energy or the gravitational potential energy is fully converted into kinetic energy of the object. Alright? And then again, if it hits the ground, then all the kinetic energy of the object, or not all of the kinetic energy of the object, is converted into gravitational potential energy again. And what can we notice about the total mechanical energy in our energy bar charts? So over time, even though the magnitudes of kinetic energy and gravitational potential energy are increasing and decreasing, so depending on what happens in the scenario, the total mechanical energy remains the same because it is the total energy of the whole system, which shows, which shows us that the amount of energy present in the system does not really change for this specific acts. So which means that force due to gravity is really an example of a conservative force. Alright, so how do we define conservative forces? So work done by a force only depends on the initial and final position of the object. So basically, we're trying to look at the initial and the final position of the objects only, regardless of the path they took. So let's look at the example present in the lower right portion of the slide. So this is the initial position, let's label that as y sub I, and this is the final position, let's label that as y sub f. The green line is the first path taken by the particle, and the blue line is the second path taken by the particle. So since we're dealing with the gravitational potential energy in here, so the gravitational potential energy in here at this point, at the final position y, is equal to the negative of the gravitational potential energy at the initial position of the particle. So regardless of the path taken by the particle, the gravitational potential energy is an evidence of the conservative force that is acting on that specific object, which is the gravitational force. So aside from gravitational force, there is also another one conservative force out of all the forces that we have discussed in the dynamics video lesson. So, and that is the spring force or the restoring force. So unlike the gravitational force that we have here, the initial and the final position of the object, for spring force or restoring force, we have the equilibrium position, which is at 0 coordinate, and then the final position will be either positive from positive displacement or the negative displacement, because there are two possible scenarios in a spring. It can either be compressed or stretched. Alright? But the main thing that we need to remember when discussing conservative forces is that they conserve mechanical energy, just like what I've shown you a while ago in the energy bar chart. Alright? So the total mechanical energy of the system is fully conserved. So let's proceed now with non-conservative forces. So we have here again the physics textbook. So let's say again that the mass of the physics textbook is 4 kilograms and the displacement is again 40 meters. So if I wanted to move this physics textbook from this point up to this point, So I wanted to move it to that direction. So this is x sub I, and this is x sub f. So this is the initial position of the object along the x-axis, and this is the final position of the object along the x-axis. So in order to move the textbook from one place to another horizontally, I need to apply a certain force, which we now call as the applied force. However, eventually, after after the motion of the book, or the motion done by the book, because it interacts on this surface, alright, so eventually the motion of the book will come to a stop. And that is because of a certain force that is present between the surfaces of these two objects. So the textbook and the surface below the textbook are interacting with one another, and that force is the friction force. We can also indicate the presence of the normal force and the gravitational force, but we don't actually need it in this scenario because they will only cancel each other out, because there's the forces along the y are balanced. However, for forces along the x, it is not technically balanced. Right? That's why the book initially moved, because the applied force is greater than the friction force. However, the book will eventually stop in its tracks because of the presence of that friction force. Alright. So now, the question is, does all the kinetic energy produced by the work done by the applied force? So again, we have here the work done by the applied force. So according to the work energy theorem, alright, according to this theorem, since we are doing some work towards a certain object, and in this case that is the textbook, we are constantly giving it some energy, and that energy is kinetic energy, because definitely the object is moving. However, the question now is, does all the kinetic energy that are present along this system is fully converted into potential energy, or was it converted into something else? So since we have here the presence of the friction force, we know that for any object that are rubbing against each other, they produce some heat, or the temperature in those surfaces are obviously changing. So they are increasing in temperature. And that increase in temperature is an evidence of the internal energy. So aside from potential energy, or from converting the kinetic energy into potential energy, some of the energy are converted into internal energy. So this internal energy will be elaborated once we are already discussing thermodynamics in general physics. However, for simplification purposes, we defined internal energy in this particular scenario as the energy associated with the temperature of the system. So definitely there is a change in the temperature of the system, because we knew that the surfaces heats up. We can say that they increase in temperature. That's why we know that there is kinetic energy that are converted into some other form of energy. So for non-conservative forces, the energy bar chart for conservative forces rather looks like this one. But for non-conservative forces, aside from potential energy, again, there is another form of energy, which is the internal energy. So this is somewhat the kind of energy bar chart that you will see when you are trying to understand non-conservative forces rather. So the kinetic energy in our bar chart looks like this one, and this is at maximum, which is equal to the total mechanical energy of the whole system. However, as the object is moving and it's interacting with a non-conservative force, the kinetic energy is obviously decreasing in magnitude. However, those energy that are converted are not literally going into potential energy as a whole. Some other energy are converted into another form of energy, which we now call as the internal energy, until such time that all of the kinetic energy are converted into internal energy. However, if we can still notice, the total mechanical energy of the system is still constant and equal all the time. So how do we define non-conservative forces? Just like what we specified a while ago, which is the friction force. So according to the slide, non-conservative forces, a transformation mechanism for energy definitely happens. So it doesn't just transform kinetic into potential or vice versa, potential to kinetic, but again, there are other forms of energy that that was formed after interacting with a non-conservative force, just like the friction force. Now, to note the difference between conservative and non-conservative forces, for non-conservative forces, they do not conserve mechanical energy. Alright, so what are the other types of non-conservative forces? So here are a few examples of non-conservative forces. So all the other friction types, kinetic friction force, static friction force, rolling, sliding friction, and even fluid friction are among all of the other types of non-conservative forces. So that also includes air resistance. Aside from air resistance, tension is also an example of a non-conservative force. So, alright, to identify faster how can we know that this type of force is a conservative force and this type of force is a non-conservative force? There are two properties of conservative forces. So if let's say a specific force qualifies for these two properties, then it is a conservative force. But if not, then definitely it's a non-conservative force. So for the first property, it mainly talks about the work done by a conservative force on a particle moving between any 2 points is independent of the path taken by the particle. So this is basically what we have mentioned a while ago, that the only thing that we care about for conservative forces are the 2 points, which is the initial position and the final position of the object. So let's say, again, let's use the example that we have in the previous video lesson. We have, for example, a paper plane, and the first path taken by the paper plane is downwards. The second path is it moves with the wind until it reaches the ground. So the question now is that is the work done different from these two particular scenarios or not? So the answer for that question is they don't differ from each other. They have the same work done. They have the same magnitude of energy or gravitational potential energy, because again, the only thing that we're trying to look at here is the initial and the final position of the particle. However, for the second property, the work done by a conservative force on a particle moving through any closed path is 0. So that basically means that the net work done by conservative forces is equal to 0, as long as the path taken by the particle is considered closed. And how do we identify if it's a closed path? If the initial position of the particle is the same as the final position of our particle. Alright, so let's try to have a demonstration for the second property. So let's say that this is the physics textbook again, and we have the same dimension, so 4 kilograms for the mass, and the displacement that would be taken by the object is again equal to 40 meters. So we're trying to look at the force due to gravity again to identify if it qualifies for the second property, to really know if it is a conservative force. And if it does not, then maybe force due to gravity is not really a conservative force. Alright, so we try to compute the work done by the gravitational force in this particular in this first movement. So the first movement is done from this point up to that point. So the only force um, acting along this motion is the force due to gravity. That's our only focus. Look at the displacement. The displacement is again downwards. Force due to gravity is downwards. So they have the same direction. So definitely the work done in here is equal to positive 1568, which is the same as the one that we already answered in the previous slides. Alright, how do we compute that again? Work is equal to FD cosine of angle theta. And since angle theta is equal to 0, cosine of 0 is equal to 1. So FD, so this is mgd, m 4 kilograms, g is 9.8 meters per second squared, and d is 40 meters, which gives us this answer. Alright, so the second motion is from this point, moving up to that point. Alright, so this is the second movement. So look at the displacement. The displacement is pointed to the right. However, the force due to gravity is still pointing downwards. So if we try to visualize that, this is the object, this is the displacement, and this is the force due to gravity. So the second question, again, if we can still remember, so we answered the first question, the direction of displacement is to the right. The second question now is to identify the magnitude of the angle theta. So in this case, the angle theta is equal to 90 degrees. And cosine of 90 degrees, so cosine of 90 degrees is equal to 0, which means that the work done in this second movement is equal to 0 joule. Right? Because any number multiplied to 0 is equal to 0. And next, the third movement is set to this motion. Alright, so it moves upward up to that point. So now the direction of displacement is upwards, but the direction of the force due to gravity is downwards, which makes the angle theta equal to 180 degrees. And then the work done at this movement or third movement is equal to negative 1568 joules. Again, because the angle theta is equal to 180, and cosine of 180 is equal to negative 1. And lastly, this is the final movement. So the final movement is from this point up to the initial position a while ago. So at this point, the displacement is pointing to the left. However, the gravitational force is still pointed downwards. So right now, the work done due to the gravitational force at this point is again equal to 0 joule. So for us to determine if it's a conservative force, according to the second property, the net work done by that specific force should be equal to 0. So let's add all the work done. So this is positive 1568 plus 0. So 1568, and then minus 1568, which yields a magnitude of 0. And lastly, we have here another 0 joule. So which makes the net work done in this particular motion of the object or the textbook equal to 0 joule. Which proves that the force due to gravity is really a conservative force. Alright, so what other things are, what cool stuffs do we see this conservative force in real life? Alright, we can see this stuff in roller coasters. So there is a possibility, alright, although we knew that the amusement parks that we tried to go on to had roller coasters in them, and the only the time that they only give power or electricity towards the ride itself is onto the first and the highest peak on the tracks that will be um, that will be seen in the whole obstacle of the roller coaster. So that is the only time that the management of the amusement park gives energy onto the roller coaster, right? Until such time that it reaches again the peak, the highest peak in the obstacle, they turn the electricity off and let the physics of roller coaster work through it. And the physics that works in this type of scenario is obviously conservative forces. So the gravitational force is the only force acting on these roller coasters. All right? And secondly, the work done, or total work done of this whole system is also equal to zero, because again, if you can still remember, if you're trying to ride a roller coaster, the first position wherein um, you ride the roller coaster is also the final position of the roller coaster, wherein you get off the roller coaster. All right, so the net work done is equal to zero, and then the time, or I mean the energy or the type of force that is used in the mechanism of the roller coaster is again conservative forces, which is mainly gravitational force. All right, so this is a good example of conservation of mechanical energy. So right now, since we're talking about conservation of mechanical energy, it is important for us to know the difference between non-isolated and isolated system. So before we proceed with identifying which type of system are we really into, let us identify first the differences between system, surrounding, boundaries, and universe. So let's say that we have here a can of a specific soda, let's say a Coke. Alright, so this is a Coke in can. So this Coke in can is the point of your observation. So all the matter and energy that is present within the Coke in can are the only thing that you are observing, or you are currently observing. So basically, your point of observation is your system. So all the matter inside the Coke is your system. Now, the boundaries, I mean the edges of the Coke in can, or the can itself, is what we call now as the boundaries, or the system boundary, because it prevents the matter from going out into from going outside the system. Alright, next, how about the other cans? So we know that not only does Coke has a can size soda, so there are also other sodas that are placed into a can, just like Sprite, Royal, and many other soft drinks or soda. All right, so how about these cans? Are they irrelevant, or are they not our system as well? So since we are not currently observing these cans, so they are considered as the surroundings. We're not saying that they are not a system. They are a system of their own. But since we are not currently observing what happens in the matter and the energy inside that specific can, so we consider them as surroundings. They might affect the system that we are currently observing, but again, since they are not our current point of observation, we consider them as the surroundings. And the combination of all the systems and surroundings that we have in here is what we call now as the universe. Alright, so let us remember all the terms that I have mentioned in this video. Alright, so we have two different types of systems based on conservation of energy. So if the total amount of energy in the system is changing, then that system is considered non-isolated. If Okay, if the total amount of energy in the system is constant, then that system is isolated. Alright, so let's try to imagine that if we're trying to boil a water inside a kettle, alright, and then that water, the boiling water inside the kettle, is filled with so much energy and internal energy as well, because it's the temperature is obviously so high. Alright, so now for non-isolated system, a kettle is a good example of a non-isolated system. Why? Because if we try to leave the water, the boiling water inside a kettle, eventually after several minutes or hours had passed, the water inside the kettle is back into its normal equilibrium temperature. Alright. However, if it's an isolated system, so let's say a thermopot. So a thermopot is not perfectly isolated, but it's a good example of isolated systems, because if we try to put the boiling water inside the thermopot, it would take some time, maybe days. Alright, maybe days, before the water inside the thermopot cools down. So yeah, those are the difference between non-isolated and isolated systems. So let's proceed first with non-isolated system. So a non-isolated system, again, is defined by this statement: energy crosses the boundary of the system through different transfer mechanisms. So since we have here different transfer mechanisms, let us identify what are these transfer mechanisms. Alright, so the first one, the stickman in here is transferring energy from his system up to the system of the box, so through work. So that is the first transfer mechanism. Second transfer mechanism is like this one. So the radio is producing sound, and sound carries energy. And sound in physics is an example of a mechanical wave. So the second one, or the second transfer mechanism, is through mechanical waves. All right. The third one. All right. So these are the greatest misconceptions, I think, in the science textbooks in elementary, because we consider these as mechanism of heat transfer. But again, heat, all right, in this context, heat is a transfer mechanism. All right, and heat is somewhat like an umbrella term for all the things that we studied and learned in our elementary school days. So conduction, convection, and radiation are good examples of heat. All right. Fourth one is through matter transfer. So just like what you can see in the GIF in here, in order for the engine of a car to work, it needs chemical through gasoline. Alright, so in order to provide that chemical energy into our engine, so we transfer that matter into from one place to another. The fifth one is through electrical transmission. So there are devices that we use inside our houses that cannot work if not for electricity. Alright, so that's it. And the last one is, of course, there are waves that do not require mediums, unlike mechanical wave. So this type of wave is what we call now as the EM wave. So EM wave radiation. So EM radiation, or electromagnetic radiation. So just like the light, the visible light. What else? All the longer wavelengths from the visible spectrum. So up until the radio waves, and all the radiation that are shorter in wavelengths from the visible spectrum up until the cosmic rays. Alright, so these are the 6 transfer mechanisms. So how do we write them into our formula? So this is the formula that was given in the previous slide. So this is delta E of the system. So this is the change in the energy of the whole system is equal to the sum of all the transfers. So the T in here is equivalent to the transfer. So the total energy of the system is basically divided into three different energies, or forms of energy rather. So we have here the change in kinetic energy plus the change in the potential energy, and again plus the change in the internal energy, because this is a non-isolated system. And what are the transfers that we mentioned earlier? So one is work, second is heat, third is transfer through mechanical wave, fourth is transfer through matter transfer, fifth is transfer through electrical transmission, and last is transfer through electromagnetic radiation. So this is the full equation that we use for non-isolated system. Alright, so I hope that you can still remember these equations if we try to answer a problem related to this type of systems. Alright, next, how about isolated system? So for isolated system, the total energy, or the change in the energy or mechanical energy of the system, is equal to 0. So this is also equal to delta E of the system is equal to 0. So what we need now to identify is if the isolated system is affected by conservative forces only, or if it's affected by non-conservative forces as well. So if it's only affected by conservative forces, then we try to compute the work done by conservative forces only. So we use the concept of the work energy theorem in order to derive the formula for work done by conservative forces. And according to this theorem, work is equal to the change in kinetic energy. And we try to write this down into this side. So for conservative forces. So if conservative forces are the only types of forces present in an isolated system, this will be the formula. So work is equal to delta K. And we knew that for every changes happening in the kinetic energy of the system, there is also changes happening in the potential energy of the system. So for every positive change in kinetic energy, there will be a negative change in potential energy. And according to our equation, the total energy of the system will be equal to 0. So we transpose negative delta U to the other side, which makes it positive. So positive delta U is equal to 0. Now, we try to expand this equation, and we knew that if you see the delta symbol, that means that there is a final minus initial in the quantity that is present. So final kinetic energy minus initial kinetic energy plus final potential energy minus initial potential energy, and that is equal to 0. And then we try to transpose all the negative signs or negative quantities into the other side of the equation to make them positive, which leaves us with this equation. So final kinetic energy plus final potential energy is equal to initial kinetic energy plus initial potential energy. Or we can summarize this into work done by conservative force final is equal to work done by conservative force initial. So this is the equation that we will be using for conservative forces in an isolated system. How about this one? So for non-conservative forces, right, for non-conservative forces, so let's use this equation again. So delta K is equal to negative delta U. However, since there is already a presence of a non-conservative force inside the isolated system, and we don't really know what type of force is, what type of non-conservative force is present. So to generalize all the work done by non-conservative force, so we try to add that into the right side of the equation. All right. So for every changes happening in the kinetic energy, there is an addition in the non-conservative force. All right. So plus work done by non-conservative force. All right. So we transpose negative delta U to the other side. So this will become delta K plus delta U is equal to work done by non-conservative force. Expand the formula again. So final kinetic energy minus initial kinetic energy plus final potential energy minus initial potential energy is equal to work done by non-conservative force. And then, alright, and then transpose these negative quantities into the right side of the equation. So final kinetic energy plus final potential energy is equal to initial kinetic energy plus initial potential energy plus work done by non-conservative force, and then summarize this equation into work done by conservative force final is equal to work done by conservative force initial plus work done by non-conservative force. Alright, and this is now our final equation for non-conservative forces in an isolated system. Alright, so I hope that you can still remember all of the equations that we have elaborated in this video lesson, because we will try to apply that when we answer some problems related to this discussion. Alright, so the last concept that we need to discuss before we finish this video lesson is about power. So power, and how does it relate to our electric bills? Alright, so according to the definition of power in the slide, the rate at which the work is done, or the rate of work and time, is considered power. So mathematically, if we try to write it down, P is equal to work done over time, or P is equal to W over T. In general, the equation of power came from these equations, wherein work is equal to the integral of P dt, or power relative to time. Alright, so now, before doing anything else, let's try to identify the SI unit present, or that is used in the quantity power. So since we have your work, and the SI unit for work is in joules, and the SI unit of time is in seconds, so the first first SI unit that you may notice as the thing that we use for power is joule per second. Alright, so how about its equivalent in fundamental units? So since joule is equal to kilogram meter squared per second squared, and then we divide that by second, by another second. Alright, so as you may see in here, so the second one that you can see for the unit of power, that is kilogram meter squared per second cube, and this is the fundamental unit equivalent of the unit joule per second, which is again a unit of power. And the last one is, of course, since most physicists and engineers wouldn't like their notes to be bombarded with so much and so many letters and units, so the unit that we use most often for power is watts, which has the symbol big letter W, which is a bummer because the quantity work also uses the same symbol. Alright, so don't be confused of the unit watts, which has the symbol W, and the unit work and the quantity work, which also has the symbol W. Alright, so why do I have here a picture of a horse? Because aside from these three SI units, before we use horsepower as a unit of power. So 1 horsepower in our modern definition of power, so 1 horsepower is equal to 746 watts. Alright, so what does 1 horsepower mean? So let's say for instance that you wanted to buy a car, and the car dealer said that the engine of the car has 30 horsepowers. So what he meant by that is that the engine is equivalent to the power of 30 standard horses. Alright, so this literally means that horsepower is really equivalent to a power exhibited by a standard horse. Alright, so that is a standard horse. Now, let's see how does it relate to our consumption of electricity. So, in general, again, as mentioned in the previous slide, the formula for power originated from this formula. Work is equal to P dt. Alright, now, all of the electric companies uses kilowatt hour as their unit for the energy consumption of a certain household. So let's write it down in here. Kilowatt hour. So one great misconception that I have observed in the previous years is that although not all of the broadcast communication or broadcast communication, um, they frequently mention the unit used by most electric companies as kilowatt per hour, which is not really of significance because again, the unit that they use is honestly kilowatt hour. So in physics terms, if we try to lower it down into what we know now as the SI unit for um, for every physical quantities that we encounter. So kilowatt is in watts or in joule per second, while R is in second. So since we have here a numerator S and a denominator S, we can cancel that one out, which leaves us with the unit joule, and we know that joule is a unit of energy. That is why electric companies use energy consumption, not power consumption, because they compute our bill using the amount of energy that we consume for 1 month. And before this type of chart is presented into our bill, before it kind of looked like this. So the time and the power. Alright, now that we have here, let's say January to February for the time frame, right? That kind of graph that you will see before is just like this one. Alright, so how does electric companies measure or compute our energy consumption? So basically, since from the original formula where power came from is that work is equal to the integral of P dt, and when we're trying to integrate something, we're basically computing the area under the curve of that of the physical quantities that we're trying to measure. So basically, we're just trying to compute for the area under the curve of this whole graph, and that is equal to your monthly energy consumption. But kudos to all the energy companies out there because they made it just like this one, because it's more accessible and more easier for a common people to understand, a common person to understand and interpret. Alright, but for us physics majors and for everyone that takes physics classes or maybe engineering classes, it would be great if we knew how to compute the energy consumption and the billing of our electricity for 1 month. And I think that will be all for this video lesson. So I hope that you learned something from this video, and we will try to apply these equations that we have derived in this video into the next video lesson, which will be about answering some problems that are related to our discussion today. So that will be all. Thank you, and see you on the next one.